A light year is an extremely familiar concept. You have seen it in movies, in books, in articles about space, so often that the brain automatically assumes it already understands what it means. But the truth is that, when understood correctly, a light year does not merely say that the universe is very far. It completely disrupts the way humans are accustomed to understanding distance. That is precisely why astronomers are forced to use it. Not to make things difficult, but to rescue intuition when talking about the universe. Distance, for humans, never begins with numbers. It begins with the body, with how many steps you have to take to leave your house, where your breathing becomes heavy on an uphill path, where you need to stop and rest. Long before maps or units of measurement existed, the brain learned to estimate distance through fatigue, time, and risk. A long journey is one that makes you consider bringing water, changing shoes, or even questioning whether you should go at all. That is why units like meters or kilometers work so smoothly in everyday life. A kilometer is not 1,000 meters. It is 10 or 15 minutes of walking at a normal pace. 5 kilometers is enough to make you think of a motorbike or a car. 200 kilometers suggests a trip lasting several hours, possibly requiring rest stops or refueling. These numbers carry meaning because they are tightly bound to lived human experience. When distances expand to national or continental scales, intuition still does not collapse. A transcontinental flight taking several hours may sound long, but it still fits within a familiar daily rhythm. You can have breakfast in one city and dinner in another, thousands of kilometers away. Even though the numbers are large, the brain can still grasp them because the journey is filled with waiting time, changing scenery beneath airplane wings, and the sensation of going somewhere, even Earth itself, with a circumference of over 40 kilometers, is not beyond imagination. Humans have circumnavigated the planet since the 16th century, taking several years, but still within the span of a human lifetime. Today, technology compresses that journey into less than 2 days of continuous flight. Earth is large, but it is a largeness confirmed by real movement and real history. And so the brain accepts it. The problem appears only when distance is no longer tied to any familiar form of travel. When there is no road, no terrain, no intermediate landmarks. When distance exists as a continuous stretch of emptiness, with nothing to break it apart. The human brain is not good at processing pure void. It needs narrative, sequences of events, a sense of progression. When those disappear, numbers begin to lose their soul. The distance from Earth to the Moon, about 384,000 kilometers, is where intuition first begins to wobble. On paper, this number is far smaller than the distances that follow. But cognitively, it is an abrupt jump. There is no journey in daily life comparable to it. No walk, no drive, no flight to anchor it. It does not feel like farther, but like something fundamentally different. When Apollo astronauts left Earth, they did not travel in the familiar sense. They accelerated to about 11 kilometers per second, hundreds of times faster than highway speeds, and then left everything familiar behind. There was no scenery passing by, no sense of moving through stages, only Earth shrinking behind them and the Moon growing ahead, across a nearly absolute emptiness. Even at such an absurd speed by human standards, the journey still took about 3 continuous days. 3 days is not the problem. The problem is what those 3 days feel like. Not 3 days moving through a space filled with content, but 3 days of waiting to cross an interval with nothing in between. Distance here is no longer a path, but time endured to arrive. At this point, human intuition begins to slip out of its own grasp. When distance is no longer filled with experience, kilometers become a cold symbol. They remain mathematically correct, but they no longer help the brain understand anything. 384,000 kilometers evokes no image, no sensation, no familiar effort. It exists only as a floating number, disconnected from life. And this is only the first step beyond Earth. If the nearest distance in space already unsettles intuition, the ones that follow will not merely shake it, they will cause it to let go entirely. Because even after accepting that some voids cannot be imagined as journeys, there remain numbers large enough to render every attempt at visualization meaningless. It is precisely at this boundary that the human brain begins searching for an escape, not by asking how far, but by changing the question to how long. When travel fails as a way of understanding, waiting becomes the measure. And from the moment that question appears, the entire way humans speak about distance in the universe begins to change. Despite consequences far greater than intuition is prepared to accept. If the moon is where intuition begins to slip, the sun is where it stops resisting. The average distance from Earth to the sun is about 150 million kilometers, a number the brain can still read fluently, but no longer attached to any experience. It evokes no image, no sensation, no effort. The number exists, but only as a pure symbol, detached from human life. What makes this striking is that the sun is not far in any ordinary cosmic sense. It is the central star of our planetary system, the driver of all biological rhythms on Earth, the energy source that makes life possible. We see it every day, feel its warmth on our skin, measure its influence through seasons and climate. The sun is deeply familiar, but the distance to it is not. 150 million kilometers resembles no journey humans have ever made. If you try to force intuition through conversion, the result becomes absurd. At Apollo, spacecraft speeds about 11 kilometers per second. A journey to the sun's distance would take more than 5 continuous months, under ideal conditions, without stopping or changing course. 5 months just to reach a distance that astronomy considers very close, even using the fastest machines humans have ever built. Intuition is not rescued. The Parker Solar Probe, the fastest spacecraft in history, can reach speeds over 190 kilometers per second near the sun through gravitational acceleration. That number surpasses anything previously achieved. Yet even so, it still takes months to complete its solar orbits. And more importantly, these numbers do not make the distance easier to understand. They only clarify the helplessness of intuition. At this point, the human brain stops trying to imagine. 150 million kilometers is not simply farther than the moon in a linear sense. It is a different category of distance altogether, beyond the reach of experience. There is no way to picture a path that long, no sequence of images sufficient to fill that void. Every journey-based comparison collapses. And when a unit of measurement no longer helps the brain understand, it becomes a burden rather than a tool. Kilometers, at this scale, do not clarify reality. They obscure it. Numbers swell beyond comparability. 150 million, 300 million, or 1 billion kilometers sound different, but they evoke nearly the same sensation: emptiness. This is the moment when the problem is no longer that the distance is large, but that the unit itself is wrong for the context. Kilometers were born to measure things humans can walk, see, or at least imagine through accumulated experience. When removed from Earth and applied to space, they remain mathematically correct but cognitively incorrect. They speak accurately, but say nothing useful to the human brain. Imagine trying to measure the distance between countries in millimeters. Technically valid, but the numbers would grow so large that no one could perceive meaningful differences. Not because distance became more complex, but because the unit became too small for the reality it describes. That is exactly what happens to kilometers in the universe. Astronomers are not people who enjoy making things confusing. On the contrary, they are forced to confront a harsh reality. If familiar units remain in use, speaking about the universe becomes meaningless, not because the universe is difficult, but because human measurement language no longer fits. And when a language can no longer describe reality, it must be replaced. This replacement does not arise from ambition, but from the survival needs of thought itself, without changing how distance is measured. Every discussion beyond Earth becomes a cascade of enormous numbers devoid of understanding. No one can compare them. No one can feel them. And eventually no one truly knows what is being discussed. That is when science is forced to do what intuition resists: change the frame of reference. Interestingly, the solution does not lie in finding a longer unit, but in changing the question. Instead of asking how many kilometers, humans begin asking how long does it take. When distance can no longer be sensed through travel, it is sensed through delay. Not how far the path is, but how long information takes to cross it. Distance begins to slip into something else that the human brain can still grasp: time. Waiting 1 second feels completely different from waiting 1 minute. 1 minute is entirely different from 1 hour. When distance is translated into time spent waiting, it suddenly regains part of the intuitive meaning it had lost. Not because it becomes smaller, but because it becomes felt. Once the question shifts from how far to how long, an absolute limit begins to reveal itself. To talk about delay, we must know what carries information through space at the fastest possible speed. Once that question is asked, light ceases to be an abstract physical concept and becomes the unavoidable standard for measuring the universe. Light enters the story not as a chosen idea, but as something that was always there, waiting to be seen in its proper role. When distance is interpreted as waiting time, all familiar speeds immediately reveal their instability. Walking, driving, flying, even space travel, all vary with conditions, technology, and biological limits. None of them are stable enough to serve as a foundation for measuring distances humans cannot directly traverse. Light is different. It needs no engine, no fuel, and is unaffected by ambition or technological constraints. In a vacuum, it always moves at the same speed, about 300,000 kilometers per second, a number that is not an estimate, but a physical constant. It does not change with location, does not depend on the observer, and has never been found to have an exception. Every fastest signal, every most fundamental piece of information, is bound by this speed. The fact that nothing travels faster than light is not a technological limitation we have yet to overcome. It is a limit built into the structure of the universe itself. There are no shortcuts, no ways to accelerate past it. All causality must line up behind light. When an event occurs somewhere in space, light is the earliest possible messenger that can carry information about it outward. From this point on, distance can no longer be separated from delay. To say that two objects are far apart is to say that a certain amount of time, irreducible and unavoidable, is required for information to travel from one to the other. Distance becomes time stretched by physical limits. Rather than a bare numerical value, a light year emerges as a natural consequence of this way of thinking. It does not describe how long an object exists, but the distance light requires a full year to travel. The corresponding number, about 9,46 trillion kilometers, can be calculated precisely, but the calculation itself is not what matters. What matters is that this distance is inseparably tied to 1 year of waiting that cannot be shortened. Using light as a ruler does not make distance easier to understand in everyday terms. It does the opposite. It forces the listener to accept that cosmic distances were never built for human intuition. Instead of trying to make the brain imagine enormous numbers, the light year offers a waiting period, a span of time that even the fastest thing in existence must obey. Light is also the only means by which the universe reaches us. Every star we see, every galaxy we image, every distant structure we study exists in human awareness only through light. Without light, there is no data. When we measure distance using light, we are using the very stream of information that connects us to the rest of the universe. This carries an unavoidable consequence. Every time we look at a distant object, what we see is not its present state, but the state it was in when the light departed. The greater the distance, the longer the delay. No observation escapes this limit. No telescope can pull the present closer. When we say a star is several light years away, that statement carries two meanings at once. First, the distance light must travel to reach us. Second, the amount of time that has passed since that light began its journey. Distance and past merge into a single unit, inseparably, at very small distances. This delay is nearly invisible in daily life, but when distances stretch to years, tens of years, and then hundreds of light years, looking far increasingly becomes looking at versions long gone. What appears before us is no longer synchronized with the observer's present. Light is not only faster than anything humans have ever built, it is so fast that ordinary comparisons become almost meaningless. In 1 second, light can travel about 300,000 kilometers, enough to circle Earth's equator more than 7.5 times. If you place familiar points like New York and Los Angeles on a map, light could travel from the East Coast to the West Coast and back dozens of times in less than the blink of an eye. A commercial jet flies at about 900 kilometers per hour, less than 0.3 kilometers per second. Compared to light, it is more than 1,000,000 times slower. The fastest car ever recorded, thrust SSC, reached about 220 kilometers per hour in its 1997 record. Yet it barely moves when placed beside light. Even machines designed for the harshest environments, like spacecraft, do not come close. Parker Solar Probe, the fastest spacecraft ever built, reached a peak speed of about 192 kilometers per second as it skimmed close to the Sun in 2023. That is fast enough to travel from Earth to the Moon in just over half an hour, and still far too slow compared to light. Even at that record speed, Parker Solar Probe reaches only about 0.64% of the speed of light. The gap between very fast and the fastest possible is not small. It is an unbridgeable abyss. It is precisely this difference that makes light the only ruler immune to technological progress. Faster airplanes will be built. More powerful spacecraft will be launched. But light does not change. It is indifferent to whatever humans invent next. It holds its position as an absolute limit. When a light switch is flipped in a room, light reaches your eyes almost instantly because the distance is measured in meters. The delay exists, but it is too small for the brain to notice. When you look at the moon, the delay is already about 1.3 seconds. This was clearly experienced during the Apollo missions. When astronauts spoke with Mission Control in Houston, each sentence took over a second to reach Earth, and the reply took another second to return. Recordings preserved to this day still carry that pause. Not hesitation, but space itself forcing a wait. The Sun, despite being our most familiar source of light, is no exception. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. When a burst of energy occurs on the sun's surface, Earth-based instruments learn about it more than 8 minutes later. If the sun were to vanish this instant, the daytime sky would remain bright for 8 more minutes before darkness fell. That brief interval alone is enough to underscore that there is no such thing as instantaneous seeing. The finite speed of light was not always obvious. For centuries, humans assumed light traveled instantaneously. It was not until 1676 that the Danish astronomer Ole Rømer presented the first evidence to the contrary. While observing the eclipses of Jupiter's moon Io, he noticed that the timing of these events varied depending on Earth's position in its orbit. When Earth was closer to Jupiter, the eclipses occurred earlier than predicted. When farther away, they occurred later. This discrepancy could only be explained if light required time to cross the additional distance. From this observation, Rømer estimated that light took about 22 minutes to cross the diameter of Earth's orbit. The number was inaccurate by modern standards, but the discovery was revolutionary. It shattered the notion that light crossed space instantaneously and paved the way for scientific measurement of its speed. By the 19th and 20th centuries, experiments using rotating mirrors, lasers, and atomic clocks had determined the speed of light to parts per million. Once light was understood to be finite, every astronomical observation acquired a new layer of meaning. Looking far became synonymous with looking into the past. Every second of delay represents a moment that cannot be retrieved. Distance is no longer empty space, but time compressed into a number. The light year is born from this realization. It does not merely prevent endless strings of kilometers. It forces the listener to remember that every distance carries an associated waiting time. An object 1 light year away is not only distant, it is being seen exactly as it existed 1 year ago. As the numbers grow, this effect becomes impossible to ignore. An object a few light years away appears as an old record. Tens of light years turn the sky into an archive. Hundreds of light years push the observer back into eras before photography, before electricity, even before many familiar historical milestones. Light, therefore, is not just what illuminates the universe. It is the only timeline humans can directly access. Each photon that reaches the eye carries the story of a moment already gone, packaged in an unchanging speed. And when light becomes the unit of measurement, distance is no longer simply near or far, but a question of how much past we are seeing at once in the night sky. When numbers begin to reach into the millions, billions, and then trillions, the human brain almost refuses to cooperate. A million already sounds large, but it still sits within a range that can be imagined with effort. A billion starts to slip away from intuition, and a trillion nearly stops being a number in any experiential sense at all. It becomes an abstract symbol. The problem is that the light year is built from exactly this kind of number. A million is 1,000 times 1,000. If you saved $1 every day, without missing a single day, it would take about 740 years to reach 1 million. That is a long time, but still one that can be placed on a historical timeline. Back to ancient Greece, when Aristotle was still teaching and Rome had not yet become an empire. A billion is 1,000 million. If instead of $1 per day you saved $1 per second, it would take about 32 continuous years to reach it. A million seconds is just over 11 days, while a billion seconds is more than 3 decades. The jump here is not linear. It is stepwise. A trillion is 1 trillion seconds, counting one number per second, without rest or sleep, would take about 700 years. When that count begins, agriculture has not yet appeared. Writing does not exist. The pyramids have not been built. the entirety of human civilization, from the first cities to modern science, fits into less than 1/3 of the time required just to count to 1,000,000,000,000. This is no longer a number to imagine, but a number that reveals the limits of imagination. 1 light-year is about 9.46 trillion kilometers long. Each of those kilometers corresponds to roughly 10 to 12 minutes of walking for a human. That means a light-year is not simply a very large number, but more than 9 trillion short journeys, each one enough to walk from home to a nearby store. When those segments are stitched together, not in familiar space, but across the near total emptiness of the universe, intuition begins to collapse. The only way to keep the brain from being overwhelmed is to construct the light year from smaller units. Step by step, 1 light second equals about 300 kilometers. Enough to travel from Earth to the Moon and nearly back again. That distance already exceeds any journey in everyday life. 1 light minute is acts in million kilometers, roughly 1/8 of the distance from Earth to the Sun. Light takes more than 8 minutes to cover that distance, and that waiting time has become common knowledge in modern astronomy. 1 light hour exceeds 1 billion kilometers. At that distance, Saturn lies at its closest orbital point, with signal transmission times of more than an hour. When the Cassini spacecraft orbited Saturn from 2004 to 2017, every image sent back to Earth carried that delay. Scientists never saw Saturn in real time. They saw it as it existed more than an hour earlier. 1 light day is about 25.9 billion kilometers. Voyager 1, launched in 1977, took more than 35 years to reach a distance roughly equal to 1 light day from Earth. When Voyager 1 crossed the heliopause in 2012, marking the first time a human-made object entered interstellar space, the signal it sent back still required nearly a full day to arrive. Even that achievement, often described as leaving the solar system, amounted to only a tiny step on the scale set by light. 1 light week pushes everything beyond the realm of familiar planets. There, the sun no longer fills the sky as a blazing disk, but shrinks into a bright point among countless other stars. 1 light month compresses the entire solar system into a very small region around an unremarkable star in the galaxy. Planets that were once distinct worlds become barely distinguishable details. Even through telescopes, when all 365 light days are combined, a full light year emerges. It is the distance light travels in more than 31 million continuous seconds, without slowing or stopping. At this scale, the solar system is no longer central to the story. Other stars begin to enter the picture as individual entities, rather than anonymous points of light. The nearest star beyond the Sun, Proxima Centauri, lies about 24 light years away. The number sounds small, just over 4 times the unit just constructed. But its physical meaning is entirely different. At the speed of Parker Solar Probe, it would take roughly 800 years to reach. When writing first appeared in Mesopotamia, a hypothetical spacecraft launched with today's best technology would still not have traveled even half the distance. The breakthrough starshot concept, announced in 2016 with the involvement of Stephen Hawking and Yuri Milner, proposes using Earth-based lasers to propel ultralight spacecraft to about 20% the speed of light. On paper, this would allow a journey to Proxima Centauri in roughly 20 years, plus more than 4 additional years for a signal to return. But achieving this would require laser systems on the order of tens of gigawatts, the ability to track gram-scale targets with extreme precision over long periods, and solutions to collisions with interstellar dust at tens of thousands of kilometers per second. Physically, the idea violates no known laws. Technologically, It pushes every existing limit to the edge. Such distances also blur the boundary between space and time. Sirius, the brightest star in the night sky, lies about 6 light-years away. The light reaching our eyes today left it before many personal events in a human lifetime ever occurred. Vega, about 25 light-years away, sends light from a time before many modern technologies existed. Betelgeuse, roughly 550 light-years distant, is seen as it existed during the European Renaissance. For stars like these, it is entirely possible that they have changed, or no longer exist at all, even though their images still hang in the sky. At this scale, the light year is not just a unit of measurement, but a reminder that every observation is historical. The night sky is not a snapshot of the present, but a layered composite of different moments, arranged by distance. Looking farther does not mean looking wider. It means looking deeper into what has already passed, photon by photon, silently bridging moments separated by years, centuries, and even millennia. As individual stars cease to stand alone in the story, the picture expands in a way deeply uncomfortable for intuition. Stars are not randomly scattered through space. They are gathered and bound by gravity into much larger structures. One of these is where humans live, the Milky Way. The name alone evokes vastness, but the numbers that accompany it are what make the light year suddenly feel appropriate. The Milky Way has a diameter of about 100,000 light years. Not a few years, not a few hundred, but 100,000 light years from edge to edge. If a photon were to leave one side of the galaxy this instant and travel straight across, it would take 100 Ws, 000 years to reach the other side. When that light began its journey, modern humans did not yet exist. Homo sapiens appeared only about 300,000 years ago. And most of our history unfolded while that photon was quietly crossing space. Within that vast region lie between 100 and 400 billion stars, depending on estimation methods and observational models. Each star may host its own planetary systems. The Sun, once considered the center of everything in ancient thought, is merely an average star, located on the edge of a spiral arm about 26,000 light-years from the galactic center. The light leaving the Milky Way's core and reaching human eyes today began its journey when humans still lived by hunting and gathering. Before agriculture, before permanent settlements, motion within the galaxy also lacks familiar rhythm. The Sun does not stand still. It orbits the Milky Way's center at about 220–230 kilometers per second. That sounds fast, but the path is immense. One full orbit takes roughly 225 to 250 million years. The last time the Sun occupied a position similar to its current one, dinosaurs were just beginning to appear on Earth. Since then, they evolved, dominated the planet, went extinct, gave way to mammals, and eventually to humans, while the Sun completed only a single revolution. Placed against that timeline, a human lifetime nearly loses all sense of motion. Over 80 years, the Sun moves only a tiny fraction of its galactic orbit, too small to perceive from the outside. The entire history of civilization, from the first writing in Mesopotamia through ancient empires, the scientific revolution, and the space age, occupies less than 0.1% of a single galactic rotation. Here, the light year no longer overwhelms. It becomes the minimum tool needed to describe movements that are slow yet immense. When viewing the Milky Way this way, ideas of travel or communication take on a different tone. 2 points. separated by only a few light years within the same galaxy, are already enough to isolate civilizations in time, at distances of tens of thousands of light years. That separation becomes absolute. Concepts of near and far lose their everyday meaning, replaced by waiting times far beyond biological lifespans. In this picture, other planetary systems appear not as potential destinations, but as isolated islands. Exoplanet surveys over recent decades have confirmed thousands of planets beyond the solar system, including notable systems like TRAPPIST-1, about 40 light-years away. This small star hosts 7 roughly Earth-sized planets, several within the zone where liquid water could exist. The light carrying information about them departed when many people alive today had not yet been born. If a civilization on one of those planets sent a radio signal toward Earth, the message would take 4 decades to arrive. A reply, sent immediately, would require another 4 decades to return. A simple exchange would span nearly a century. In that time, both societies could change completely. Technologically and culturally, communication would no longer resemble dialogue, but the reading of letters from previous generations. These constraints make science fiction ideas like faster-than-light travel deeply appealing. Warp drives, wormholes, and shortcuts through space are often presented as promises of liberation from isolation. But when set against tested physical principles, the problem lies not in imagination, but in energy, causality, and the structure of space-time itself. Relativity allows time to dilate as velocity increases, but it also erects an unbreakable barrier. Reaching the speed of light requires infinite energy. These limits are not technical details to be solved with better materials or stronger engines. They are woven into the fabric of the universe. And when the Milky Way is viewed as a single unit, the light year fully reveals its role, not just as a measure of distance, but as a measure of separation between stories that exist in parallel yet never touch. From this perspective, the silence of the night sky takes on a different meaning, not because nothing is there, but because everything there is separated by waiting times too long to become shared experience. Stars within the same galaxy may share material origins, but they do not share a present. Each stellar system is its own fragment of time, drifting through the same space but never synchronized. When the galaxy ceases to be an abstract mass and instead becomes a place containing hundreds of billions of stars, a question almost automatically arises. Is anyone living around those stars? For most of history, this was purely philosophical speculation. It was not until 1992 that astronomers first detected planets outside the solar system, while observing small, unusual oscillations around a neutron star. In 1995, the first planet orbiting a sun-like star was confirmed, and from that point on, the picture began to change rapidly. By the mid-2020s, more than 5,000 exoplanets had been confirmed, with thousands of additional candidates awaiting verification. These planets are not clustered in some distant corner, but are spread throughout the Milky Way. A large fraction orbit red dwarf stars, which make up about 70% of all stars in the galaxy. This has made the existence of rocky worlds, and even worlds with conditions somewhat similar to Earth, far more common than previously assumed. The TRAPPIST-1 system is a frequently cited example. Its host star is much smaller and cooler than the Sun, yet it has 7 roughly Earth-sized planets orbiting it. 3 of these lie within the zone where liquid water could exist on the surface. The entire system is located about 40 light-years from Earth. The light carrying information about those planets began its journey when the world did not yet have widespread internet access, and arrived at a time when near-instant data transfer has become routine. This distance is not merely an astronomical number. It defines the nature of every attempt at communication. Radio waves, like light, travel at a finite speed. A signal sent from Earth toward TRAPPIST, one would take 4 decades to arrive. A reply, if one exists, would require another 4 decades to return. A simpler question, even in the best-case scenario, becomes an exchange lasting nearly a human lifetime, even in closer cases. These delays shatter intuition about communication. Proxima Centauri, the nearest star beyond the Sun, lies 24 light-years away. A message sent when a child is born may return only when that person reaches middle age. There is no concept of conversation, no immediate feedback, no real-time adjustment. Each message is a slice of the past, sent with the hope that the recipient still exists to read it. This fragility undermines the idea of an interstellar civilization functioning like human society on Earth. Politics, economics, and culture all depend on rapid feedback. Decisions can be adjusted in days, hours, or even seconds. When distance is measured in light years, all such structures collapse. No central authority can effectively govern communities separated by tens of light years. Each world must be autonomous, not by ideological choice, but by physics. Scientists have long imagined scenarios of interstellar settlement, where humans leave the solar system to establish colonies around other stars, even assuming technology allows travel at 10% the speed of light. The journey to Proxima Centauri would still take more than 40 years. That is long enough to turn a trip into a lifetime commitment. Those who depart would never return, and those who remain would grow old while the ship is still crossing the void between stars. In this context, the concept of a simultaneous civilization becomes blurred. Two societies, separated by a few dozen light years, never truly live in the same present. When one sends information about its condition, the other receives only an outdated record. If conflict, misunderstanding, or even simple cultural divergence arise, there is no mechanism for rapid correction. Every response arrives late, often too late. Even passive observation is inherently historical. When modern telescopes analyze an exoplanet's atmosphere in search of biosignatures, the data reflects that planet's state in the past. If a civilization has just emerged, or just disappeared, the light carrying information about that event may still be in transit. Every discovery is an inference drawn from fragments already out of sync with reality. This creates a very different picture of a life-bearing universe. Not a vibrant network of civilizations in constant exchange, but a collection of time islands, each operating on its own rhythm, separated by waiting periods that cannot be shortened. Somewhere in the Milky Way, across millions of years of biological history, many societies may have arisen, flourished, and vanished without ever knowing of one another's existence. This isolation does not arise from the rarity of life, but from the structure of space and time. A light year does not merely measure distance between stars. It measures the difficulty of overlapping stories. Two civilizations may exist within the same galaxy, yet never share a single moment. They exist in parallel, but out of phase. Viewed from this perspective, humanity's search for extraterrestrial signals takes on a different tone. Programs like SETI listen to the sky, searching for artificial patterns amid natural noise. But even if a signal were detected, it could be the echo of a society that no longer exists. Any encounter, if it occurs at all, would resemble archaeology more than communication, deciphering messages from those who are no longer there to reply. When faced with distances measured in light years and delays stretching across decades or centuries, the natural human reflex is to look for shortcuts. If light takes too long to travel from one place to another, the immediate idea is obvious. move faster than light. In science fiction, this is almost the default solution. Space bends, a gateway opens, or a warp drive engages, and distance ceases to be an obstacle. The problem is that physics does not operate on narrative intuition. In the 20th century, Einstein's special relativity established an unavoidable rule. The speed of light is not merely fast, it is an absolute limit. It is not a record waiting to be broken, but a constant tied to the structure of space-time itself. As an object with mass accelerates and approaches the speed of light, the energy required to increase its speed no longer grows linearly, but exponentially, approaching infinity. This is not theoretical speculation. Modern particle accelerators, like the Large Hadron Collider, have pushed tiny particles to 999,999% of the speed of light. At that threshold, adding energy does not significantly increase their speed. It only increases their inertia. There is no smooth path to crossing the light barrier by simply pushing harder. Reaching the speed of light requires infinite energy, and the universe does not supply infinity to anything with mass. From here, ideas for circumventing the limit begin to appear. One of the most famous is the warp drive, proposed by Miguel Alcubierre in 1994 as a mathematical solution to Einstein's equations. The idea does not require the spacecraft itself to move faster than light. Instead, space in front of the ship is compressed. Space behind it is expanded, and the ship slides inside a bubble of space-time. On paper, the effective speed can exceed light without locally violating the limit. However, this mathematical solution comes at an enormous cost. Creating such regions of compressed and expanded space would require a form of matter with negative energy density, something never observed on macroscopic scales. Early estimates suggested the energy required could be equivalent to the mass of an entire planet, or even Jupiter itself, just to move a small spacecraft. Later refinements reduced the energy requirement, but it remains far beyond any conceivable technological capability. Wormholes present another frequently discussed idea. They appear naturally in certain solutions of general relativity, describing tunnels connecting distant regions of spacetime. If they exist and can be stabilized, a wormhole could allow travel between points separated by thousands of light-years in a very short time. But once again, the problem lies not in mathematics, but in physical reality. The wormholes described in theory tend to collapse as soon as they form. Keeping them open would again require exotic matter with negative energy. Moreover, wormholes raise severe issues of causality. If one can travel from point A to point B faster than light, then in some reference frames, this is equivalent to traveling backward in time. Time paradoxes emerge immediately, from causal loops to the possibility of disrupting the very sequence of events that allows the journey to exist in the first place. Relativity does not forbid such solutions on paper, but it also does not promise that they can exist in the real universe. The gap between what is mathematically allowed and what the universe actually permits is vast. Throughout the history of science, many elegant solutions have been discarded because they conflicted with observation. Warp drives and wormholes currently occupy this gray zone, not explicitly forbidden, but with no evidence that they can be realized. Another consequence of approaching the speed of light is time dilation. A clock aboard a fast-moving spacecraft runs slower than one at rest. This effect has been measured with extreme precision using atomic clocks on GPS satellites. Without correcting for time dilation, global positioning systems would drift by kilometers within hours. Near light speed, the effect becomes extreme. A journey lasting only a few years for those aboard the ship could correspond to decades or even centuries for those who remain behind. This opens scenarios that sound appealing, traveling to distant stars within a short personal time. But the cost is a complete rupture with all social reference points. Anyone who returns would arrive in a profoundly changed world. People they knew may be gone. Language, culture, and technology may no longer be familiar, even without violating physical laws. This is not a solution to communication or interstellar community. It is simply a one-way displacement through time. When all these factors are placed side by side, the picture becomes clearer. Science fiction often assumes that distance is merely a technical obstacle that will eventually be overcome. Modern physics suggests the opposite. Distances measured in light years are a direct consequence of how the universe is built. They are tied to the speed of light, to the structure of space-time, to causality itself. This is not a wall that technology can break through, but the skeletal framework of reality. This does not render interstellar stories meaningless, but it places them where they belong, as hypotheses, as thought experiments, as tools for understanding the limits of the real world. When we return our gaze to the night sky, the light year is no longer just a distant unit of measure, but an expression of a deeper order. It says that the universe allows diversity, allows life, but does not promise closeness. If space is that vast, if even light requires billions of years to cross its deepest voids, then how large is the part of the universe that humans can actually see? Not the entire universe, but the region that light has had time to reach us from, carrying information out of the deep past. All the limits discussed so far converge on a simple but uncomfortable question. How much of the universe are we actually seeing? The answer is not all of it, but a very specific portion, determined by the speed of light and the age of the universe. The universe is currently estimated to be about 13.8 billion years old. That means the oldest light that can reach us today departed at that time. No earlier. It seems reasonable to think that we should only be able to see as far as 13.8 billion light years. But reality is more complex. While light has been traveling, space itself has been expanding. Galaxies are not standing still waiting for light to arrive. They are being carried farther away while that light is en route. As a result, the radius of the observable universe is not 13.8 billion, but about 46.5 billion light years, forming a sphere nearly 93 billion light years in diameter. Within this immense volume lies everything humans can, in principle, observe. Galaxies detected by the Hubble Space Telescope and the James Webb Space Telescope at distances greater than 13 billion light-years reveal the universe when it was very young, only a few hundred million years after the Big Bang. These images are not snapshots of the present, but historical records, documenting the formation of the first stars and galaxies. Beyond this boundary lies a concept known as the cosmic horizon. It is not a physical wall, but an information limit. There are regions of space receding from us so rapidly that light emitted there will never reach Earth, even if we wait trillions of years. Not because light is slow, but because the distance grows too quickly. Those regions exist, but are cut off from all possibility of observation and interaction. This creates a perceptual paradox. The universe may be far larger than what we see, possibly infinite. But for humans, only the observable region has empirical meaning. Any theory about what lies beyond the cosmic horizon cannot be directly tested. It may be true or false, but light will never deliver the answer. In this picture, the light year is no longer just a ruler for measuring distances between stars or galaxies. It becomes a tool for defining the boundary of knowledge. Each additional light year corresponds to a deeper layer of the past, and ultimately to a past that cannot be reached at all. The observable universe is not the central part of reality. but the part whose light managed to tell its story to us in time. When we look into the depths of the sky, what humans actually see is not infinite space, but a bubble of information expanding along with time. Every galaxy within it is connected to us by a single thread. Light that crossed the void and arrived before space could pull it too far away. And it is this very limit that sets the stage for the final, most unsettling question. If the universe is so vast, if there are countless places light has never reached, then what does the silence we observe truly mean? When the number of stars in the Milky Way is estimated to reach into the hundreds of billions, and when exoplanets show that rocky worlds are not rare, an apparently obvious question becomes haunting. If life and intelligence are not rare, then where is everyone? Enrico Fermi posed this question in a remarkably simple way. In 1950, during a lunchtime conversation with colleagues, where is everybody? Not as a dramatic challenge, but as a logical discomfort with a universe that appears too quiet. Over the decades, many explanations have been proposed. Perhaps life is rarer than we think. Perhaps intelligence self-destructs before it can spread. Perhaps civilizations choose to remain hidden. But when the light year is placed at the center of the problem, another possibility emerges. Less dramatic, but more persistent. Distance and time have made each other's existence nearly irrelevant. A civilization that lasts a few thousand years is extraordinarily durable by Earth's standards. But a few thousand years is only a blink of an eye on galactic timescales. If two civilizations are separated by thousands of light years, the probability that both exist long enough for light to cross the distance between them is already very low. One may have vanished long before the other's signal ever arrives. Even in the most optimistic case, where two civilizations coexist and transmit signals, the light year still turns communication into a game of delay. A message sent is not a greeting, but a civilizational will. The sender does not know who will receive it, when it will be received, or whether its context will still be understood. The receiver, if one exists, reads a slice of the past, not an invitation to dialogue. This makes the universe's silence far less mysterious. It need not be evidence of absolute loneliness, but rather a natural consequence of space that is too vast and communication that is too slow. Civilizations may arise, develop, decline, and disappear like brief flashes against the backdrop of cosmic time, rarely overlapping long enough to recognize one another. Search programs for extraterrestrial signals, such as SETI, continue to scan the sky, listening for non-random patterns. But even if a signal were detected, it would most likely be the remnant of a civilization that no longer exists. Any encounter, if it occurs at all, would resemble excavation more than a handshake. The light year does not forbid life, but it makes simultaneity a rare exception. In this context, the Fermi paradox is no longer the question, why don't we see anyone? But was it ever reasonable to expect to see one another at all? The universe may be full of stories, but each is written at a different tempo, at a different time, separated by waiting periods that cannot be crossed. Silence is not necessarily emptiness. It is distance, turning time into an invisible wall. When we say that humans are small in the universe, this is not a poetic statement. Earth has a radius of about 6,300 kilometers, orbits a star 109 times larger in diameter, sits in a galaxy roughly 100,000 light years across, and that galaxy is only one among hundreds of billions in the observable universe. Light from the most distant galaxies observed by the James Webb Space Telescope departed more than 13 billion years ago, when Earth did not yet exist. These numbers are not meant to overwhelm, but to locate humanity accurately on the map of reality. And yet, Within this context, the fact that humans can understand the light year at all is remarkable. Just over a century ago, in 1923, Edwin Hubble confirmed that the spiral nebulae were actually galaxies beyond the Milky Way. Before that, the entire universe was thought to be contained within a single galaxy. Less than 100 years later, humans not only know that there are hundreds of billions of galaxies, but have measured the observable universe to be about 93 billion light-years across. Based on the cosmic microwave background and models of cosmic expansion, the light year is the tool that makes all of this possible. Without it, every measurement would collapse into meaningless strings of kilometers. With the light year, it becomes possible to say that the light from the galaxy GNZ 11 departed when the universe was only about 400 million years old, or that the signal Voyager 1 sends back to Earth today takes more than 22 hours to arrive, even though the spacecraft is only about 0.002 light-years away. Small and large numbers coexist within a single, unified frame of reference. Even the universe's silence can be placed on a concrete, measurable foundation. The Drake equation, proposed by Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the Milky Way, but every variable in that equation is governed by one underlying factor: distance measured in light years. A civilization that lasts 10,000 years sounds long-lived, but compared to the time light needs to cross the galaxy, it is only a thin slice. The light year does not deny the possibility of other life. It shows how small the probability is that those stories ever overlap. The fact that humans can even ask such questions and answer them with observational data is rare. The temperature of the cosmic microwave background is measured at about 725 Kelvin. The age of the universe is estimated at 13.8 billion years, with uncertainties of only a few tens of millions of years. Distances to nearby stars are determined by parallax, with precision down to fractions of a light year. These are not philosophical speculations, but the result of expanding human understanding far beyond the demands of survival. The light year, therefore, is not just a distance. It is proof that humans can understand things they will never physically reach. A species that lives less than a century on a small planet can still measure a universe stretching tens of billions of light years. Small, but not meaningless. Not because we are at the center, but because we are curious enough and patient enough to understand something vastly larger than ourselves. When distance is measured in light years, the almost instinctive human reaction is to look for shortcuts. If we cannot go faster, then perhaps we can bend the path. From that intuition arise concepts like faster-than-light travel, warp drives, and wormholes, not first in science fiction, but in serious physical equations. In 1905, Einstein published special relativity, and just 1 year later, physicists accepted an uncomfortable consequence. The speed of light, about 299,792 kilometers per second, is not the fastest speed technology has yet failed to reach, but a constant built into the structure of space-time. The evidence does not come from distant space. Right here on Earth, particle accelerators like the Large Hadron Collider have pushed protons to 99.9999991% of the speed of light. The remaining difference, even at the level of parts per million, requires an explosive increase in energy. As velocity approaches c, the energy required does not increase linearly but tends toward infinity. This is not a technical limitation, but a mathematical barrier. No finite energy source can accelerate a massive object to, or beyond, c. Warp drives are often mentioned as an escape route. In 1994, Miguel Alcubierre identified a solution to Einstein's equations, in which space contracts in front of an object and expands behind it, allowing it to move faster than light without violating relativity locally. The problem lies in what is required to make this happen. The solution demands negative energy density, a form of exotic matter never observed in nature. Early estimates suggested energy equivalent to the mass of Jupiter. Later refinements reduced this to several times Earth's mass. But it remains far beyond any experimentally realistic possibility. Wormholes, or Einstein-Rosen bridges, appeared earlier. In 1935, they allowed two distant points in space-time to be connected by a short tunnel. Mathematics permits their existence, but physics is less forgiving. Simulations show that natural wormholes would collapse almost instantly. Keeping them open would again require negative energy and structural stability far beyond what ordinary matter can provide. There is also the problem of causality. A wormhole stable long enough would almost certainly allow backward time travel, leading to logical paradoxes that modern physics has no way to resolve. The crucial point is this: none of these concepts are rejected because technology is not advanced enough. They collide with deeper limits tied directly to the structure of reality itself. The light year is therefore not just a measure of distance, but a measure of what can and cannot happen. It tells us not only how far away something is, but how far is too far for familiar ideas of travel, communication, and presence to survive. After all the numbers, all the distances stretched until intuition fractures, the light year leaves behind a strangely quiet feeling. It does not only make Earth feel smaller, it makes human time feel more fragile. A human life lasts a few decades, while light from Sirius takes 6 years to reach us. From Vega, 25 years. From Betelgeuse, more than 500 years. When we look at the night sky, what we see is not the present universe, but slices of time that passed long ago. That easily leads to a pessimistic conclusion. Humans are too small, too slow, too isolated to matter in a universe tens of billions of light years wide. But this is precisely where the light year reverses the story. To measure those distances, to know that the Milky Way is about 100,000 light years across and contains between 100 and 400 billion stars. To infer that the observable universe is roughly 93 billion light years in diameter, humans had to build a system of understanding far beyond survival instinct. This is not something a small and meaningless species accomplishes by accident. The light year is proof that the human mind, though evolved to avoid predators and find water, can extend its reach to things it will never touch. No one will travel a full light year. No one will reach the edge of the observable universe. Yet humans can measure it, describe it, and test it through observation and mathematics, knowing that light has a finite speed, that the universe is about 13.8 billion years old, that space is expanding at an accelerating rate due to dark energy. None of this provides direct survival benefits. Yet it stands as an intellectual achievement at the scale of a species. The light year also forces humanity to confront real limits. Not everything can be overcome by technology. Not every distance can be shortened by will. Some boundaries are woven directly into the fabric of space-time. But rather than making everything hopeless, this makes what does exist more precious. If every civilization is a time island separated by tens or hundreds of light years, then the fact that intelligent life arises, persists, and understands the universe around it is an event rare enough to be valued. In the end, the light year is not just a unit of astronomy. It is a fusion of distance, time, limitation, and connection. It reminds us that when we look up at the sky, we are receiving information from a deep past, from stars that may have changed or no longer exist, and within the brief moment of a human lifetime. Understanding that fact is already a way of touching the universe. Humans are small, yes, but humans can understand what is vast, and in a cold, wide, indifferent universe stretched out in light years. That capacity for understanding is meaning in itself.